So, in Alice in Wonderland, Alice would spend all morning thinking of 12 impossible things. We're going to show you today, me and my lab, that nothing is impossible. And actually, if you put your mind to it, things can be inherently possible, even if you think that it's incredibly difficult. Nothing is too hard. So, we're going to start off today with a pussycat, because we're going to merge two odd fields for you. We're going to look at cell signaling and hairballs. So, what's a hairball, and what the hell has it got to do with cell signaling? We'll find out. So, in 10 seconds, in every cell in your body, there are 1 million chemical reactions. This is an estimate, right? 1 million chemical reactions every 10 seconds between 42 million proteins in every single cell. And you're made up of probably 14 to 15 trillion cells. So that's a lot of stuff to deal with. So, your cat having a good cough gives you this, a nice juicy hairball. But in data science, we think about this. So, mapping all of those protein interactions in a single cell of the trillion cells in your body gives you something like this. We also call it a hairball. Basically, it's an oversaturation of data. Protein binding protein. 1 million interactions every 10 seconds. It is almost insane levels of activity. So, the important thing is, can we find order in the chaos? We're not interested in mapping chaos. We're interested in deconvoluting, reducing what's called dimensionality of data. When you have this amount of data points, its number of dimensions, the number in ways in which you can compare point to point, are way in excess of the number of molecules in the known universe. Way in excess. So, simply looking at protein-protein interactions in a single cell is beyond our comprehension at the current times. So how on earth do we think about aging across the whole body for many years? So we need to think about how we understand complexity and how we understand order. So the wonderful thing is there is always beautiful order, even in hypercomplex systems. This is one of my favorite examples of it. So here, look at this beautiful pattern that's spreading across the screen. Now, what you're looking at here is tracings of a single person pushing a push bike all the way across a room. And it's being mapped 862 times. Now, you think where the bike ends up is where that trail goes. You'd think it'd be random, but it's not. Because the bike has a uniform shape. It has a single function and a single shape. Its random effects end up being very ordered because of a mechanism of the bike retains its structure. What happens to it is still affected by its intrinsic structure.